Okay, hopefully that went fairly well and you got some sort of band of stability kind of graphed out for your elements. Your graph is not like a perfectly straight line. It should kind of start out at one angle and then up near the top be at a slightly different angle. What we actually find is that down here and the lower part of atomic numbers of protons, the stable arrangement is to have the same number of protons as we do neutrons. So something like nitrogen with an atomic number of 7 is stable when it's got a mass of 14. So 7 protons, 7 neutrons. Oxygen, number 8 on the periodic table, that has a weight of approximately 16. So until we get up to approximately atomic number 20, we have our proton and neutrons in a 1-to-1 ratio, and that seems to be the stable arrangement. As we get higher up on the periodic table, higher atomic numbers, number of protons on the periodic table, it kind of changes. And once we get up here a ways, it's actually a 1.5-to-1 ratio, meaning we have to have 1.5 times the number of neutrons as we do protons. So if we had a situation where we had 80 protons, we would need 1.5 times that of neutrons to make it stable. So we'd need approximately 120 neutrons to go with 80 protons to make it stable. You do reach a point, and I probably should erase part of my line, but you do reach a point at which no number of neutrons is going to make it stable. So once we get above lead, number 82 on the periodic table, there is no number of neutrons that will make something stable. So everything on the periodic table past lead is radioactive, is unstable. It's going to do some sort of a decay. There's not enough of that strong nuclear force. The nucleus is just too big. It will eventually fall apart and decay, actually change into something new. So the nucleus will break apart. For some things, it may be very slow. It may break apart instantaneously, and other things are almost instantaneously. So the speed has nothing to do with it. We'll talk about the speed later when we talk about half-life. But we have this 1-to-1 ratio up to approximately atomic number 20. And then as we get to higher numbers, it's about a 1.5-to-1 ratio. And after lead, no number of neutrons is going to do it, and they're going to all be unstable. So that's our band of stability. If we're above our band, we need to lose some neutrons. If we're below our band, we need to add some neutrons. We've got to make some shifts in order to get there. So we call this process of getting there decay, and it's radioactive decay. So decay implying that it's going to fall apart, and it's going to do this on our own. And we have lots of different forms of decay, and I've put more forms on my board than you're really going to need to know. We focus mostly on the first two. So all these decay things are just changing our neutron to proton ratio. So we're doing something, we're having a change to the nucleus occur to get a more stable ratio. The first one is called alpha decay, and this is going to decrease both the number of protons and the number of neutrons. So if you have a really heavy element and it might go through the alpha decay to sort of lose protons and neutrons both fairly quickly. So their symbol for alpha is this kind, I don't know, it looks almost like a Jesus fish a little bit. That the symbol with the 4 and the 2, meaning a total mass of 4 and a total number of 2 protons. But that's also the same as a helium nucleus. Again, we're not dealing with electrons. We're just talking about the nucleus. So you'll see this alpha particle written this way, 4/2 alpha or 4/2 helium, and we just call it an alpha particle. So if a substance goes through alpha decay, it would release one of these particles. It would break apart into one of these particles and something else. So alpha decay, big old heavy particle, and as far as particles would go for decay. Another one is beta decay, and beta is going to change our number of neutrons. And again, I'm not real concerned that you can say which one does what. Our symbol for beta is this 0, -1, and then this beta symbol. Again, a decay breaking apart in this, we're going to look at some examples in just a second. It's a much smaller particle, and we're going to look at that. And we'll talk about the strengths of these particles as well. This is not one that we do much with, but I want to at least introduce you to it, and it's something called positron emission. So a positron is kind of like a positive electron. So same mass as an electron, but it has a positive charge. So we think of a proton as being able to break itself apart into neutrons and positrons. And I know that's kind of out there of what we've talked about, but the protons and the neutrons are made up of smaller particles, and so a proton can be changed into a neutron. And now we're violating all the rules we never thought we would ever violate. The symbol for it is a lot like our beta. It's 0, but it's a +1. And again, we don't do much with this, but I want to show you that. The other type of decay, and it's kind of a little odd, is called electron capture. Now this one, this electron is actually a reactant. The others, those particles, the alpha particle, the beta particle, or a positron, those are products. If we were writing a chemical equation and showing it, we would have them on the product side. Electron capture is kind of weird. So again, we've totally ignored all the electrons outside the nucleus. Electron capture is a case where one of those electrons from outside the nucleus gets captured, sucked into by the nucleus. So maybe one of those first electrons closest to the nucleus gets taken and actually put into the nucleus. And it is combined with a proton to make a neutron. So kind of weird thing there. We're taking an electron and a proton, putting them together, and we're creating a neutron. So if something needed extra neutrons, maybe it would do this. The symbol for it looks just exactly like our beta particle symbol, but again, it's capturing it, so it's going to be on the reactant side instead of giving it off and being on the product side. When you have electron capture, X-rays are often given off as like another form of radiation. X-rays do not have a, oh, hang on.